So welcome everyone to session 4. In this session now we learn about the neural network architecture, the mathematical model of neural network, and the backpropagation algorithm, which is as I said before, is the main learning and training algorithm for deep learning or deep networks. So deep feed-forward neural networks are the first proposed neural network architecture. It's also called multi-layer perceptron, and or also it's called an MLP. The main goal of neural network is basically to approximate some function. It's called universal function approximator. What the meaning of that? We have a data set. We have, as we have seen, let's say we have some input features, and these input features, they have a relationship with an output. This output could be a class in terms of classification, or it could be a value, continuous value in terms of regression. The neural network, what it does, is try to approximate a function that maps this input to that output. So this is why it's called function approximation, and it's called universal function approximation because it's generic for any type of functions, linear, nonlinear, or whatever the function is. So in feed-forward networks, this is what the meaning of feed-forward basically. That means that the propagation of data or propagation of information goes from the input layer, which is here where we have the feature space, to the output layer directly without any recurrent or feedback connections. We will see later when it comes to now recurrent neural networks like LSTM or other type of neural networks. There we have some feedbacks. Feedback, for example, from the output of neuron to itself, or feedback from the last layer to the first layer. So this is not a feed-forward network. In that case, it is basically a recurrent neural network. So the information through the function being evaluated from X through the intermediate, basically computations, which are the intermediate hidden layer, to the output Y. We have seen in the XOR example, or the exclusive OR, that we have two inputs. We have here the logical, we had actually two logical functions, which is the AND and OR. This is the first hidden layer, and we have one output layer. As I said, in the feed-forward, there is no feedback connections. Now, this was the beginning, feed-forward architecture, but now we really have many architectures, as we'll see later, that basically they are diverged from this architecture. So the mathematical model of neural network is very important and also very simple. So usually when you look at neural network papers, there is the architecture, which is usually presented like a drawn architecture. And many, if you have experience in network, you can understand the underlying model when you look at the architecture of the model. But also the mathematical model is very important, of course. And the feed-forward neural network has the simplest mathematical model. We have seen the lecture before, and the lectures before, actually, not the only one, that we have the model or the mathematical model of single neuron. And we said that is like a linear model because we have kind of inputs. For example, let's look here at the X, just because in that lecture we had X as an input. This is the input layer. It's considered as a layer of neural network, but it's called input layer. And we have then hidden layers, and this is, for example, layer 2, which is the hidden layer and has the index 2. So the index 1 is always the input layer there. So we have seen that we have a linear mathematical model for the neuron because we said that we multiply the weights with the inputs plus the second weight with the second input plus the third weight with the third input. So all the connections, they are weighted with these weights or coefficients multiplied by the weight. And we have seen that we have a bias, which actually originated by also the threshold we have seen that represent how the biological neurons work. Now, There's something important to know, that every neuron in, for example, hidden layer 2 or hidden layer L is connected to all the neurons in the layer before. So you can see we have connections to all the neurons in the layer before, and this is mainly for the feedforward neural network. As I said, there are many architectures. In these architectures, basically people try to change, maybe disconnect or connect, but for the feedforward network, all the neurons from the layer before are connected to neurons in the second layer. So this is basically something important to know. We can see that now the output neuron here is connected to all the neurons in the layer before. This +1 represents the bias, as I said, which would be multiplied always by this B1 here. Sometimes also you can choose not using bias. These all hyperparameters that you need to do during the model selection, which for that we need to use a cross-validation strategy, as we have seen in the lecture before this one. So all neurons are connected. All neurons, they have weights. These weights, let's say, they represent how important the connection is in some way. So it depends on the learning strategy, but basically, if you compare to the biological neurons, the higher the weight is, the more important. But of course, now in real scenarios, there could be some negative weights, positive weights, and so on. But of course, if the weight is 0, that means this connection is not important at all, because the learning algorithm decided to cut this connection. Now, so this is the linear model inside. So neural network is not only linear, of course, nonlinear approximation. So we need to have some nonlinearity in the model. And of course, the threshold model that we have seen, it's also a nonlinear model, because it has two parts. It has a threshold that if it's smaller than the threshold, then the output is 0, otherwise it's 1. So this was one nonlinear model there. But as we'll see in the next lecture, which is about the comparison between activation functions, and because in gradient descent is the main algorithm to train your network, and because gradient descent requires the functions to be basically that we can differentiate these functions. For example, the threshold, we cannot differentiate it. It's not differentiable function. That's why we cannot use it. So this is why there are some approximation of that, which is called sigmoid. We'll see it later. But the thing here, this f is basically called the activation function, and the simplest version of it is the threshold function that we have seen. So this is the general model of general neural model, and here it says that the neuron A. So this here A is the activation, so which means the output of a neuron. So the I here is the index of that neuron inside that layer. For example, here 1, 2, 3. These are the 3 neurons in this layer 2. L is the index of the layer. Okay. Then here we have the F, which is the activation functions. Now, for example, for neuron 3, now we need to do the weighted sum of all the output of the neurons before. For example, here we are multiplying the weights that are basically connecting here now. So J is a source, which means the index of the neurons from the layer before. I is the sink here, or the index of this neuron, because here we have I, you see. And J is the index from the neuron before, multiplied by the output of that neuron from the layer before. So here L minus 1 means the layer before. So this is the general model of the activation, or actually of the neural model, one neuron general model. So this is the general model, as we've seen. Now we have some terminologies there. The model that before the activation, which is the input to the activation function, which is in between these two brackets here, is called the activation model. So everything that is before applying the F function. It's usually denoted by Z here. It also has the index of the neuron and the index of the layer. We have the activation function. One of them is the sigmoid. So one of the forms that f can take is sigmoid function. We will see it later in the next lecture. But sigmoid is one of the simplest, one of the oldest as well. And as I said, is a mathematical approximation of the threshold function. Here the advantage that is more smooth and also can be differentiated, because for the backpropagation, for the training, as I said, we need to have different differentiable functions. So here we have the activation, or actually the output model, as I've said before. Y is the ground truth. So for example, we'll see that later. This Y means the real data set, okay? That means for the supervised learning, we have said that we have input and we have output for the training data. We have examples of inputs and outputs, and Y here represent the real output. Now, HWX, which is the hypothesis here, using the W's, which are the weights as a function of X, is the output of the neural network, so the final output of the neural network. Because we have output of neurons, we have output of that neurons, for example, we have the output of the final neuron, which is the output of the neural network. Then we have the cost function. As I said, we have different cost functions, but here we can look now at the basically mean squared error here, or the second norm here. We have the difference between the ground truth and the output of the neural network. So chain model is very important to understand how backpropagation works. And if you are familiar with calculus, and you should know what a chain model is. Basically, it's a chain model of differentiable equations or differentiable functions. And the idea here, if we have, for example, a list of functions like we see here in case of the neural network, because we have, as I said before, the activation model, which is what is inside this f function here, is a function of the weights, right? Because the inputs samples, as I said, which is x, and the outputs are known. These are our data. What is unknown now in our model is the weights, the parameters, and this is basically now z is a function of w. The activation alpha is a function of z itself, because now we have f there. And of course, the cost function at the end is a function of the activation. So of course, the cost function is also a function of the weight. But this is how the chain is basically, because start with the pre-activation or the activation model, the output of the activation, and then the cost function. We have seen that the gradient descent is given by the basically the weights. The current weight actually update, or the next weight is equal to the current weight minus the learning rate multiplied by the partial derivative of the cost function with respect to that weight. So here it means we have a layer L. This is the weight at layer L connecting the neuron J to neuron I. So if you look back here and the model, we have seen, for example, this is now the W2, which is, for example, from the layer 2, connecting the neuron 1 at layer 2 to neuron 1 at layer 3. So this is our gradient descent. And now we need, of course, because J here is not only, so J is a function of W, but in the way to W, there are other functions. And what we need to do is basically to build a chain model of that path that we have here, or that graph that we have here. And the idea basically here, this is basically what we can do. It's known in the differentiating functions. So, for example, the first derivative or the partial derivative of J with respect to W is equal to partial derivative of J with respect to alpha, because this is the first one here, multiplied by the first derivative of alpha with respect to z, multiplied by the first derivative, partial derivative always with respect to w. Okay, so this actually, if we, for example, this is the same here and this is the same here, they actually can vanish. But if we organize them in this way, we can now estimate the derivative, the first derivative and the second derivative and the third derivative, independently, and then we can multiply them to get the final gradient that we need to update the weights using gradient descent. So we start with the basically this part, the last part here, which is the first partial derivative of z with respect to w or omega, or not, yeah, w. And here basically this part of the chain. So the first derivative of z with respect to w, this is the z function, right? And in this sum or weighted sum, we have multiple w's there because k here vary from 1 till r, which is the number of neurons in the layer b4 and in the layer l-1. One of these weights is actually our target weight, which is j, okay? And only this part where there's j can have derivative. The rest would be equal to 0, right? Because they are not a function of that ij. So if we estimate the first derivative of that, we would get actually everything else would vanish except this part, this element of this sum, which is ij multiplied by alpha j. And so if we estimate the first derivative of that, this would actually equal to 1, and this we get a alpha j l minus 1. So this is the first part of the chain model. It's very simple. Now we move to the second part, which is now basically alpha as a function of z. So we need to estimate the activation actually as an output, or as a basically respect to z here. That depends now on the activation function we are using. So if we are using sigmoid, it has a basically first derivative. All the activation functions, we know their derivatives. This y, of course, as I said before, the activation function needs to be differentiable, because if it's not differentiable, this is a chain, we cannot do it, so we cannot do the training, we cannot do gradient descent. So what we have here then is basically the first derivative of f, which is the activation function with respect to z. This is our f, right? And usually for sigmoid, basically, this is what is you can estimate that easily. This is basically the first derivative, which means it's equal to 1 over 1 plus the exponential of minus z, which is this part, multiplied by 1 minus again f. So this is basically our, here there should be extra bracket. This is our first derivative of that activation function. Now here, what is it's a bit more complicated, or it becomes more complicated, but not that complicated, because here we have the activation now, and the cost of respect to activation. Here it depends where this neuron is located. For example, if this neuron is the output neuron, like here, then yes, it has direct impact on the cost, because the cost actually is calculated there at the output. If this neuron is in the hidden layer, then here we have the chain is different, because we have a next now neuron in that chain model. So we have two actually option, or two actually ways to calculate this this cost, or this part of the chain. If L is the output layer, then it's easy, which means this neuron is the output neuron. Then we have here to differentiate the cost function. This also again why the cost function need to be differentiable. The activation functions need to be differentiable, the cost function need to be differentiable here as well. And of course the pre-activation function needs to be differentiable. So all these three should be differentiable. So this is our cost function, and you can also easily estimate that, for example, for the mean square error, this would be the first derivative of the mean square error. This if it is an output layer. Now, if L is a hidden layer, it's something else, as I said, because this is the neuron. This is basically the next neurons would be. So this is the neurons in the L minus 1. Don't be confused here. The propagation of inputs or actually data is from this direction to that direction. So the knowledge, as I said, is coming from right to left, the data, but this is now I just reversed here because the chain model is in the opposite direction of how the data flow, because the data flow from right to left also here, because this is actually the weight that multiplied by the input. Then we have the pre-activation, then activation, then the costs or the output as well. And this is basically now just the same. So we have neuron, then the next neurons, then maybe the costs here, if these are the output neurons. So how to deal with this then? Of course, these functions now, or these neurons here, are a function of the output of that neuron alpha IL. So the cost or the derivative of actually J with respect to alpha is again the sum of basically derivatives now of J with respect to IK L minus 1, this one, multiplied by alpha K, again this one, over the alpha IL here, plus next one, add next one. So this is basically now the chain in between the J and alpha IL there. So we have a sum, the same as where we calculated the first derivative with respect to omega or here W. If we take, for example, now these parts, which is important, the derivative, which is basically connecting two neurons to each other, either these two or these two or these two. The first derivative or the partial derivative of alpha k L plus 1 over alpha IL here. You can see it there. Looking at because here we have these weights, right? That is connecting now this first weight, second weight, and the third weight here. Again, only the one element of that sum that actually connecting K with I, K L plus 1 with IL, is the important one, which will be Ki. So we will get here WKI, and the rest would be equal to 0, would vanish. And here, actually this will go as well, of course, because of the alpha here. And then we get WKI. So we can replace this part then with this sum of the first derivative of the cost over AKL plus 1 multiplied by WKIL, okay, which we get it from there. So this I again here, the index of that, K is the index of the neuron in the layer L plus 1. So it could be 1, 2, or R here. So now we're still not finished. If usually we denote now in the neural network, we denote this part here actually, which is the cost of J over alpha IL with delta IL here. So what you see, what you would see basically there, what we have here, delta IL at the layer L is equal to the sum here of the delta KL minus L plus 1, sorry, multiplied by the WKIL. So this is basically now the last part of the chain. If, as I said, if there's an output layer, then this would be the final gradient of this neural network. This neuron, actually, it's the neuron of the neural network, the neural part. And if L is the hidden layer, then this would be the final gradient of that hidden layer. So now the backpropagation, how it works then. I mean, it's a gradient descent, and the most important part of it, of course, is the cost function, how we can differentiate the cost function, because we need to get the gradient. So what we do there, first we perform forward pass, which means we apply the data set on the neural network, we get the outputs, then we estimate the cost, of course, And then for the output layer, we start because with the end, all of the training, it's called backpropagation because we start from the last layer and then we backpropagate. So starting from the last layer, we have here the condition. If it is an output layer, we calculate the gradient using this model that we get to. And now for all the hidden layers now, for all the neurons that are in the hidden layer, we use that function that we have estimated. It's backpropagation because you need to get this for layer L plus 1 in order to get it for layer L. Okay, so it's going layer by layer from the output one, then the one before, then the one before until we reach the input. Then we update the weights for each neuron, for each weight actually in each layer and for each neuron. So here basically taking now the cost function for all the neurons individually, or the gradient of every neuron individually, or every weight actually individually, multiplied by the learning rate. This is how we update the weights. And as we have seen the gradient descent session, we repeat that until either we get to one of the stopping criteria as either that we convert, which means the error is not improving, or the performance is not improving anymore, and the error is not actually decreased anymore, or if we reach maximum iteration, like after 1,000 iterations, we stop doing that and we are done. So if you want to look at this, basically you can access the slides file, not the PDF, and you can find the Python code for the backpropagation algorithm. It's not important for this one. If you are registered in the lab, then we will have a look at this later. So it's a simple but a bit complex at the same time. It's simple if you just look at it several times, then you can understand what is happening. But in general, it's all about actually this chain model. Okay, you have to estimate that and that and that, and then multiply them together, and you get the gradient, and then the rest is gradient descent. So there are different, let's say, variants of gradient descent or backpropagation. All these variants are about how to estimate the learning rate, because as I said, if the learning rate is too big, for example, we might lose the global minimum or even local minima. If the loss is too, or the learning rate is too small, then it takes too long to learn. So this is basically the trade-off. There are many variants of the gradient or the backpropagation. I will basically in the next lectures we will see them, but they are all about how we can adopt and estimate the learning rate. Thank you.